Okay, so let's go ahead and get started here. Uh, well, last time I talked about two-dimensional kinematics, and we're going to continue with that discussion here. But what I want to do today is to kind of work through some examples of this stuff. I know that I gave you kind of a brief overview last time and went through the notes, and I know that we went through that pretty quickly. And that was to give you kind of a general sense of what we're going to be doing. What I want to do for the next lecture or two is just work some practical examples. These are going to be very, very similar to what you're going to see in the homework. They're going to be very, very similar to what you see on the test. So what I've done here is I've given you a couple of equations that I think you should remember. You should write these down because I'm going to be going back to these equations several times. And because I have limited space on the whiteboard with frame of reference for the camera, I'm going to have to refer to these. So it'll probably help you during the next couple of lectures. You just take a minute to write these down. And if we remember, this first one is our general equation for position. Now, a lot of times in your book or in the notes, you might see this as x equal x naught plus b naught equals 1/2 ac squared. I use in this case, the generic S for position for displacement. It doesn't really matter. The S notation is more generic. Just remember that this means whatever direction we're talking about. So we're going to see that we're going to need X and Y components of things. So we're going to have to get into that. And I'll show you how to convert the X and Y component from the general form. But for now, you know that one. And you know the equation for velocity, in this case, is just v naught p plus at. Or, sorry, just v naught plus a. So the equation for acceleration in this case is trivial. It's just acceleration is acceleration, because nothing we're doing in this class has to do with time-dependent acceleration. They're all going to be constant acceleration problems. So we don't really have to worry about that. Remember that if we have a vector A, it is comprised of an X component and a Y. Say again?
Sorry, I was 5 minutes late. My phone was updating.
Oh,
I couldn't get in.
You fail. No, that's fine. So if we have any given vector A, it has an X component and a Y component. So if we remember what that looks like, here we have some vector A. I generally will put this little arrow on the top to indicate that it's a vector. For what you're doing right now, that's not going to make too much of a difference, but it is a good habit to get interested to start doing, because it will help you as you get more advanced. So we have this vector A. Now I'm going to say, just arbitrarily, I have chosen a coordinate system that we're used to seeing, where X is positive to the right and Y is positive up. Well, if we try to describe this vector in what direction it's pointing a little bit in the X and a little bit in the Y. Now that's very difficult to deal with, because we're used to thinking of these kind of one-dimensional linear things. So the easier thing to do is to understand that this vector A has an X component called A sub X and a Y component called A sub Y, where the X component is the cosine of the angle between your primary vector A And the X component, in this case, theta represents this angle here. So doing some trig, as we covered a couple of lectures ago, it's pretty trivial to see that the magnitude of the X part of the vector a sub x is the cosine function of whatever this angle is times the entire vector. Similarly with y, the y component is the sine of the angle times the vector. So just this is going to be crucial for you to understand in order to do the next kind of problems again. So let me go ahead and do an example here. This is an example that is in the notes. It's the place I stopped talking last time. But we're going to go ahead and work some things on the board with it. So what it's given you is we have a standard XY plot arranged in our usual convenient coordinate system. And we have some firework artillery shell that gets fired with some velocity v naught. Remember, anytime we use the sub-zero, that naught, that means initial. So this firework or cannonball or whatever it is fired with an initial velocity when it leaves the launcher of v naught, whatever that is. It's not going to change. It's not going to accelerate. It's probably going to decelerate because of gravity. But there's no rocket motor, there's nothing else propelling this thing. And so we also know that this thing is fired at some angle theta. Now, one thing that I want to show you with this, I have intentionally drawn the trajectory of this firework thing as a curve. Now that doesn't really work with our triangle model because we're used to triangles being these kind of straight edge things. In this case, because we're going to be dealing with such small estimates, it's okay to think about the velocity as being something that looks closer to a straight line. Now you can see that this approximation is really great down here early in the flight. But as we get towards the top, we start to get this deviation. The only way that you can account for this accurately is to split this thing up into very, very small pieces so that the arc is a flat line. If you make this small enough, that'll be a flat line. You'll have a whole bunch of little triangles, you add them together. That's tedious. Unless you know calculus. And that's one of the purposes of calculus is to be able to account for that curve instead of having to approximate as a triangle. Again, outside the scope of this course. This is an algebra-based course. So we're not going to be worried too much about the curvature. We're just going to model this as if it were a straight line. So in the notes, it gives you some detail here. And the way that it's written in the notes is it says that we launched this thing and we know because the manufacturer told us that the shell is going to explode at the highest point in its trajectory. And we happen to know that the highest point happens to be 233 meters. So we can just kind of draw this. That's 233 meters. we know that if we look at downrange from wherever we launch this thing, the distance along the ground is going to be 125 meters. So we have to ask ourselves now, what can we find from the information that we're given? Ultimately, I would really like to know how fast this thing is coming out of here, right? Now, why might I want to know that? That's probably a more practical problem. If I'm setting up this fireworks display, and I know that my crowd is 125 meters away from wherever I'm shooting this thing off, and I want to make sure that I get a particular altitude. Well, maybe I don't want 233 meters. Maybe I want this to be 150 meters. I want it to be closer. Or it's dangerous. I want it to be higher up. The only thing that we can do to modify and change that is going to be this angle. We can't do anything about the velocity that thing comes out at. But if we want to be able to start adjusting that angle, we need to know what that velocity is in the first place. So how are we going to do that? Well, it's actually pretty easy. We can find, first of all, this angle. So remember what we have here, if we think of this as a right triangle, with the right angle being here, then that means our hypotenuse is out here. And our adjacent side is down here, our opposite side is over here. We need an angle, and we know two sides. Well, simple trig. Remember, if I do my SOHCAHTOA thing, some old hippie caught another hippie tripping on acid. Remember, those represent our sine, cosine, tangent, and our opposite, adjacent, hypotenuse sides. So we have to think about what we have. We know an adjacent side, we know an opposite side. Here's a function called tangent that has the opposite side over the adjacent side. And we know those. So tan theta is the opposite side, which is going to be 233 over the adjacent side, which is 125. Those are both in meters. The meters are going to go away. Make sure you check that. Check your units. Remember what we're expecting. We are expecting an angle. The angle should not be in meters. The angle should be in degrees or radians. I can look at this right now and give you a pretty good guess of what this angle is, just the way I've drawn this. It's certainly not going to be 90 degrees. Certainly not going to be 0 degrees. It's going to be somewhere between 0 and 90. Well, the way I've drawn this, a good thing to do is to kind of visualize what would halfway look like. Because half of the angle between 0 and 90, by definition, is 45. So if I look at this thing and I kind of visualize a 45-degree angle, I can see that what I've drawn for my visa knot here is going to be a little bit bigger than 45. Now, I don't know that for sure. I might have eyeballed this incorrectly. I might have not drawn it to scale. But assuming that I'm pretty close on my scale, I can already get a good sense of what the answer should be. So we plug in everything we know, our units cancel. We're going to end up with something that's just in terms of theta, which is fine because that's what we want. And if you do this math correctly, then what you find out is that angle ends up being about 75 degrees. If you come out with something different than that, there's usually two reasons that happens. Number one is you might have messed up a sign. So if one of these was a negative direction, you'd probably get something a little bit different. That's not the case here. You could have missed a decimal place. If you miss a decimal place on any one of these calculations, you should expect to see your answer be different by a factor of 10. So in this case, if I'm expecting something like 75 degrees, if I'm off by a factor of 10, this might end up being 750, or it might be 7.5. So that's a good indication that you made an error with a magnitude of function. The final thing, and the more common thing you're going to see when you plug this in your calculator, if you have not put this thing in terms of degrees, this is going to come out in radians, and it's going to be some strange decimal number. It's going to like point, I don't know what that would end up being.
Yeah, I had a problem putting that
Yeah.
in my calculator. I had to do it a couple of times before I got it right.
Yeah. Yeah, it's a little
Yeah.
tricky. Remember,
Yeah, it is.
or you need to be in degrees,
Okay.
because I expect what you were getting when you were doing that problem, I expect you were running into exactly that, right? You were doing these calculations, you were getting some really funky value, like 0.3 or something.
Yeah, it was like 0.000 and then a few numbers after and stuff.
So that's a good indication that you're in radians mode. Because
Okay.
there's no way in hell that angle is going to be almost zero, right? So
Yeah, that's
something
not.
went wrong and you're off by several orders of magnitude, that's generally an indication that you're not in degree mode. Now, if you do this and you come out with something like 73.4 or something, yeah, close enough. Again, we're estimating here. So, what can we do with this information? We know what the angle is. Remember, ultimately what I'm trying to find is I'd like to know how fast V naught is. So, let me erase some of this. I know that theta is 75 degrees. Ultimately, what we want is V naught, so we'll just call that V. Now we know that's a vector. So we know that V has to be equal to the X component and the Y component of this thing. Well, how do I get that? A couple of different ways. Let's not do velocity just yet, because we don't know anything about time. But what I can do is I can find out what this diagonal distance is. I could do this, right? If I want to do it this way, then I know my X component magnitude is 125. Well, remember earlier that your X component is the cosine of the angle times the total vector. In this case, we know what the X component is. 0.5 equals cosine theta. Well, we know theta is 75. A. So that means that A must be 125 over cosine 75 degrees. Whatever that works out to be. There's an easier way. Recognize this is a right triangle. Well, if our diagonal here is the hypotenuse, and we know two sides, we can just use Pythagorean theorem, right? C squared is a squared plus b squared. We know what a and b are, plug them in. And you'll work out whatever that distance is. I haven't done it, but it's trivial. It's a good little exercise for you to do. So what else can I do with this? Notice how I'm building some kind of functions here, right? I'm building some tools. Also, I want you to notice that this is a common thing you're going to see in physics problems. As you work the problems, write down the pieces that you solve, because we're going to use those pieces later. Just like here, we first found out what that angle is. Remember, I didn't give you that angle. I gave you the two distances. We had to solve for that angle. We found it. Now, once I have theta, now I can start using functions that have theta in it. Remembering that this is an x component, a y component. Okay, cool. Let's do something else with this. Now let's start trying to find these velocities. How am I going to do that? I'm not given any information about the velocity of this projectile as it leaves the launcher. I'm not giving any information about how much time it takes for this thing to reach the top of the arc. So we might say that we're screwed, but we're not. There is an assumption that you can always make unless I tell you otherwise. And that assumption is that we're doing these experiments on Earth, or at least around an object with a gravitational mass equivalent of the Earth. Back to our spherical count vacuum problem, we're not worried about air resistance. We're not worried about the morphology of the object. Morphology is a fancy physics word for shape, by the way. We don't know anything about that, and we don't care. So what can we do with that information? I now know my theta. I know some distance. It's cool. But I want to start thinking about velocities. Velocities in particular, and accelerations by design, are functions of time. So I need to know something about time. Well, if we go back to our initial kinematics equations, we'd like to know something about time. So we look at these equations. Let's see if we can use the first one about position, because it was pretty easy to find whatever the total length of that vector was. So that would be our final position. Well, now I have a problem, right? Because this is generic. This doesn't tell me anything about if I'm worried about X direction or Y direction. So I have to make an assumption. Let's just pick a direction. Let's say it's the Y direction. So this would mean final position in the Y, which we know, I don't know what we calculated that to be, 233 meters. S naught would be S naught sub Y, right? That would be our initial position in the Y. Conveniently, we chose it to be 0. So that goes away. Our V naught now is generic, right? Now this gets a V naught sub Y, for example, or X, if you're looking at X direction. And so you might go, well, what the hell does V naught Y look like? Well, V naught Y looks like the Y component of that vector. So it looks like the sine of the angle times the magnitude of the entire acceleration in the Y direction, or the entire velocity in the Y direction. And then that time. And then finally, we have a 1/2 AT squared. this is not going to work for us because we don't know anything about that initial velocity in the y direction. It's got some initial velocity, but we don't know what it is. We don't know anything about the total velocity of the thing. So we've got a v naught y that we can't do anything about, and we've got this t that we can't do anything about. So that equation's not going to help us. We need something else. Well, we can do some cleverness here. And we can recognize, we can go back to the last chapter. We were talking about throwing baseballs straight up in the air. I had you throw your pen in the air and kind of watch it. And we know that at the top of the arc, that thing is going to stop. So that means at the top of the arc, this thing's final velocity has to be 0. Not the initial velocity. Remember, the initial velocity is some positive value. It goes up in the air and it has to turn around and come back down. So when it turns around, its initial velocity is 0. So we can say that 0 equals whatever v naught is. Still don't know that. Plus the acceleration. This is where you have to be clever and think about physics. What is causing the acceleration of this thing in the y direction? There is not a rocket motor on this thing. So the only acceleration that is acting on this is the acceleration due to gravity. And remember, in our coordinate system, we use 9.81 as the magnitude. And because we've chosen up as the positive direction, gravity is going to act in the downward direction. So we have to add in this negative 9.81. Remember the negative speed distance. And then we need to know our time. Okay. That's interesting. We're getting somewhere now, right? Well, I can almost solve this for v naught, but I need something else. Other thing that I need, I really need something that is time independent. So this is where I asked you earlier to go in and on your own try to find the time independent equation of motion. The way you do that is we want an expression for v naught that's just by itself. So if we rearrange this, we get v naught equals v minus at. Since we know v naught is v minus at, we can plug that in here. Now watch what happens when we do that. What you're going to end up with, if you work this algebra through, is all these t's are going to go away. They're going to cancel. And we're going to end up with a nice expression for our v naught. Now I'm not going to work through this whole thing because that gets a little nasty. I'm going to do a different example here in a minute where we're actually going to use things in terms of velocity and do the same kind of thing. The reason I show you this is because I want you thinking about how do we use the equations. A very common mistake that I see with all of my entry physics students, you come from an environment, probably in your high school, where if you had physics, more than likely, you learned physics as here's a whole bunch of equations, and you were probably given a formula sheet, and you kind of learned patterns. You kind of learned to look for variables, plug them in, and not really think about what it meant. Notice that if we slow down and we kind of take this thing apart, we start recognizing what the equation means. So when we're making substitutions like this v naught substitution here, for example, we're not just randomly plugging things in, we have a purpose. We're trying to get things in terms of one variable. This AX, AY thing has a purpose now. It's not just, oh, every vector does that. It's because, oh, I need an X and a Y component. Cool. So we can use this to dig in and start finding things. Now, I might be able to give you something like this on a test and then give you the initial velocity of the projectile. You can see how, if I made this a test question, this might be 5 or 6 questions in one, right? I could give you points for correctly drawing the free body diagram. I can give you points for setting up your equations correctly. And I can make it more and more complex, and I can make it build on itself. This is kind of what I want you to be expecting. I've been thinking about how to do the testing in this class. Don't hold me to this. I have not completely solidified this yet. But I think what I'm going to do is the majority of your test is going to be online. It'll look just like the homeworks. In fact, I'm going to take most of the questions directly from the homework. That test, it'll be 100% grade test. But the amount of points you can get from the test just by doing the multiple choice is probably going to be about 80 or 90. So where are the other 10, 15 points going to come from? There will probably be one question that I will ask you to write down on a piece of paper, scan it, and send it to me, showing me where you've done your work. I'm doing this for a couple reasons. Number one, I don't want you to beat your head against the wall on every problem trying to figure out how to do this. Number two, if you go through the test and you can do everything perfectly on the multiple choice and data entry parts of it, I can be pretty confident that you know how to do this. You're going to end up with a low A, but still an A. That's risky. I wouldn't just stop there. More than likely, you're going to miss a few, and that's okay. And this is a great way for you to demonstrate to me, hey, I know how to do this. Or at least I have the general understanding of how to do it. Plus, me caveman, me stupid, me physicist, me lazy. I got 28 students enrolled in this class. I don't want to make a 10 question test where every problem is draw this, write these equations, because now I have 280 questions that I have to dig through that are all going to tell me the same thing. So it's easier on both of it if I just kind of give you one. But it's not going to be very complex. If you can understand this, you'll be fine. Let me go to another example. Anybody have any questions, by the way, on that before I move away from it? Should probably bring up the chat.
No, don't.
Okay. So. Set up the next problem. Oh, by the way, I did put the next homework assignment for this piece up on WebAssign, and I've made it due a week from Wednesday. And there's only 2 sub assignments now. I gave you 3 last week. And I think that was probably a little much for some of you to get through, because I think some of you are still struggling with this a little bit. So I only gave you 2 sub assignments, so you have a little less work and you have a little more time to work on. My intent is for you to get through those, have those due a week from Wednesday, and then a week from Friday, I'll probably do the first test. In between now and then, remember, my office is always open to you. Just email me or something and tell me when you'd like to come by so I can make sure I'm there. So here, the first thing we're going to discover is that there's a reason I went into physics and not art. Pretend this is a volcano. It ejects some rock at a velocity of 25 meters per second. We're going to pick a horizontal from the top of the volcano. And we're going to say that it makes an angle of 35 degrees. So we want to find out some things. We want to find out if we have this projectile it's going to land somewhere out here. So we'd like to know how far away that is, right? Because what if there's a fishing village or something out on the coast of Hawaii, and you'd kind of like to tell them that, oh, there's this giant rock. Or, you know, if something really unreasonable and crazy happens, like let's say that, I don't know, there's a spy balloon that, I don't know, let's say China decided to fly and we shoot it down and it's going to fall on people. You'd kind of like know where it lands, right? That's crazy. That would never happen. We also need to know a little bit of something about how tall the volcano is. So let's say it's 20 meters. Now here's a trick that we can do that should make our life a little bit easier. If we assume the top of the volcano is our 0 point, then that means the distance from our horizontal at the top to the ground is going to be negative 20 meters. Or because we picked this to be 0. So anything below that line's got to be negative. Now I can start doing some interesting things. I know an initial velocity. I know that this is on some Earth-like system. So I kind of inherently know that our acceleration in the y direction is negative 9.81 meters per second squared. Another quick caution about units. I tend, when I'm doing these problems on the board for you guys, to omit the units because I know that the units are correct and match up. You really should be writing units because if you memorize the acceleration due to gravity is minus 9.81 meters per second squared, and you get in a habit of not writing meters per second squared, if I gave you this distance, but instead of in meters, I gave it to you in feet. So that's going to be roughly, what, 36 feet or so? Or no, sorry, 66 feet. So if I give you this is in 66 feet and you use 9.81 meters per second squared, your number is going to be all screwed up because you're not using the right units. But here, conveniently, we have meters, time's going to be in seconds. We're fine. So now I start finding out some things. I go back to my initial equation. We're going to have the same problem if we try to find this distance here. Initially, this total x. Because we're not going to know too much about our initial velocities in the x and y direction. We're only going to know the diagonal. So we need to start getting some component vectors out of this thing. Well, this is where we can use that trick that the total velocity is going to be our Vy plus AT. I know the or sorry, final velocity is initial velocity. Acceleration. I know my final velocity is 0 at the top of the arc. Yeah. So that's got to be 0. My initial velocity I know is 25 meters per second. Plus my acceleration, don't forget the negative sign, times time. So that means that minus 25 meters per second divided by minus 9.81 seconds gives you time. Sorry, that's meters per second squared. My units right. Meter is going to go away. 1 of the seconds is going to go away. We end up with something that looks like 25 or negative 25 divided by a negative 9.81. For the sake of math, to make this easier, let's call the acceleration due to gravity a minus 10 for now. So that'd be negative 25 divided by negative 10 should give you a 2.5. Notice the negative sign goes away. Which it should, because we're measuring time. So I know the entire time that it takes to get from here to here is 2.5 seconds. That's cool. Well, what happens if I want to know how far this distance is? Well, that's going to be my x component. So I need the x component of this total velocity. So I know my v sub x is just v cos theta. I want v sub x. I know v is 25 meters per second. I know theta is 35. So you can work this out. I don't know what it is off the top of my head. We'll get a value for v sub x. Well, what can I do with that? Since I know v sub x now, and I know t, now I can say my x position equals my initial x position plus my initial velocity in the x direction times plus my a in the x direction times t squared. We can do a couple of things here. I'm trying to find this x. My x naught is going to be 0. My v naught in the x direction I'm going to have to find, but I know t. And my t, what did I say? It was 2.5 seconds. What about the acceleration in the x direction? What do we know about that? It's 0. Remember the difference between velocity and acceleration. Velocity is how fast the thing's going. Acceleration is how quickly it's changing speed. There is no rocket engine on this thing, so it is not accelerating in the x direction. So the acceleration in the x direction is 0. So that whole term goes to 0. Well, remember our x is v cos theta, which we just found is the same thing as 25 cosine 5 degrees, which we plug in there and we find is our total distance x traveled, but that's only to the halfway point. Because there are no other forces acting on this thing, if we double that, we'll get this is our 2x. We also know at that point, the velocity at this point has got to be 0. Or at least our y position has got to be 0, because that's our origin. And then we now have a problem that we had in the very first equation here, or in the very first chapter, where effectively we're just dropping a ball off a building that's 20 meters high. And we can find the time it takes to do that. We could certainly calculate all of this, right? And we could certainly find what these total distances are. But not a huge deal. It looks intimidating at first. I know it's tedious and intimidating the first time you do it. But I promise you, if you go back to these equations and work through it, this is all you're ever gonna need for these problems. Just work these equations. Look, all this thing is a right triangle problem. All it is. All we've done today is right triangle problems. Guess what we're going to do Wednesday? We're going to do more right triangle problems. We're going to get a little more complex with them, but I'm going to do more of this. This is really the core of what I want you to get out of this first section of Physics 1, everything up to the first test. This is a core skill. This is a core concept that you're really going to need to understand, because this is going to come back to you in E&M when we start talking about electric circuits, we start talking about magnetic fields and directions, if we start talking about momentum. Certainly towards the end of the semester, we're going to get into rotational motion. So instead of throwing rocks off a building, we're now going to have a rock tied to a string. We're going to swing it around in a circle. And we need to understand how these vectors work in order to do those kind of problems. So this is why we're starting here, and that's why this is important. All right. So I think I have run my suck for long enough today. Does anybody have any questions before we quit for today?
No, just don't make the exam hard.
If you can understand this, you'll be fine on the exam. If you understand homework, you'll be fine on the exam.
Cool.
My objective in this class is not to punish you. Well, unnecessarily. I usually do that just for fun, but I really do want you to succeed, and I really do want you to understand this stuff. And I also understand that the first time you see this is hard. There's no way around it. I'm not going to make the exam so hard that you cannot pass it. That's easy to do. I am not going to make the exam so easy that you can come in hungover 20 minutes late and knock it out. So I want it to be somewhere in the middle. And remember, what I'm really looking for is that. I'm looking for continuous improvement. I'm looking for effort. So use the homeworks. That's where I'm going to draw a lot of things from. Go back and watch this lecture. Understand how to do these problems. The exam is going to be no surprise. It's going to be exactly the stuff I've been doing. Okay. Anything else? Okay, then that's where I will stop today, and I will see you guys on Wednesday.